or block to keep things simple for you. And it's represented by a branch. And the second component is you have a node, right, which is drawn as a small circle. And this node represents a signal, right? So this is called a node, right? So for a basic representation, let me just draw something to show something. So if you have this right here, and you have a system or block with a transfer function g of s, and it moves out this way. To represent this in a signal flow terms, I'll first of all have to identify the signal over here. Let's call it A, and the signal over here, let's call it B, right? Then, based on what I've done so far, it's not following. It means very difficult to. Okay, so this is a signal, this is a signal. So how are we going to represent it here? Like I said, signals are always represented by a node. So the first thing you do is to draw a node here, and then another node here. And then always make sure to label your signals. So this signal belongs, this node belongs to signal A, and that node belongs to signal B, right? And then always the system is being represented by a branch. So the branch connects the two nodes together and gets this. And then you always have to write the transfer function over there. So this is just the basic representation of how you would convert a transfer function or a block reduction that or a block diagram into a signal. Do you remember the three forms of block diagrams? If you check the previous videos, you actually see the three forms. Right? The first form is the cascaded form. I don't know why this thing. The first form is the cascaded form. Right? You set the cascaded forms in such a way that if you have at least two blocks or systems being cascaded together to actually give you a diagram. So if you have the first system here with a transfer function of G1 of S, and the second one with a transfer function of G2 of S, and the third one with a transfer function of G3 of S. Then you have the input signal, let's call it R of S. There's an internal signal. This one is an internal signal. And then the output signal, let's call it C of S. Now there's a way for us to represent the cascaded form in signal flow graph form. So the easiest way to do it is to first identify your signals, right? So we've identified this particular signal as our input signal and this one as our output signal. Now we have to name our internal signals, right? You can actually choose any name that you want. I'm going with A, B, and C, and so forth. So I'll name this signal here A, and I'll name this signal here B, right? So the first step is to try to identify the signals, right? And then draw them in terms of signal flow graph something. So the first signal here is the R of S here. So I draw it a node. And the second one is the A that I've named. So let me name this node R of S. And then the second node is A, right? With a signal A. And then the third node is B with a signal B. And then the output node is this and C of S. Now, the second thing is to draw my branches. So branches represent the system or the block. So the first branch is this. Then I take notes of the direction. So the direction shows the direction of the signal through the system or the block, right? So the name of this branch that I've just drawn here is the transfer function, which is G1 of S. Likewise, so I can draw the same thing too for the G2 of S block, which is like this, in G2 of S. Now I can do the same thing too for the G3 of S. The direction there in G3 of S. Right, so this is the signal flow graph equivalent of a cascaded form when it's not being converted into the signal flow graph. So we have the inputs here, we have the transfer function of the first block, the internal signal A, the transfer function of the second block, the internal signal B, the transfer function of the third block, and then finally the output signal, which is C of S. The second form that we'd like to treat is the parallel form. So we already know that the parallel form has summing junctions in there and then a pickoff point. So let me just draw an illustration here. I have this. We're all conversant to this already, so there's no need to explain what's going on. G2 S G3 of S. Summing junction here. There is plus or minus. This side is plus or minus. Actually depends. So this input signal is R of S. Then the output signal is also have a C of S. So the first thing to do is, first of all, take note of your signals, right? So let's take note of the signals here. So the signal here is R of S. And since this side is a pickoff point, then it means that what you have here too is R of S. What you have here too is R of S. And what you have here too is R of S. Now, this signal is an internal signal, which we have to name ourselves, right? So let's name this internal signal A, and let's name this internal signal B, and let's name this internal signal C, right? This output, this the output signal, it already has a name, C of S. So how then do we, draw this? Like I said, we have to, first of all, identify the signals and then draw the nodes first. So the first signal that's here is the input signal, R of S. So I first of all draw the node for it. Then I write the name by its side. Then the second signal are these inputs, are these internal signals, your A, B, and C. So let me draw them as they appear here. So the A is on top. So you have your node. Then I write the A there, node, the name of the node A. Then the B continues. The B is below the A. So B, node B. And then the C2 is below the B and it follows that way, node C. Now, the next signal that we have is the output signal, which is C of S. So we just draw it in alignment with the R of S and B, just to make our whole thing nice. So node and C of S. Now the next thing to identify is the system or the blocks. And in the parallel form, the system here is the G1 of S. The block with the G1 of S transfer function, this block with the G2 of S, transfer function and this block with the G3 of S transfer function. So we have to draw it in, in spatial, we have to draw it with respect to how they appear this here. So this block connects the input signal to this internal signal A, right? So we just stick it like that, stick it from the RFS node and then connect it to the node A. And then we have to show the direction of the signal, right? So it's flowing in this direction. And then you have to name the branch. And then the only way to name the branch is with the transfer function. So it's J1 of S, right? And then we do the same thing too for this side. So for this system with the transfer function of G2 of S, we can see that it's actually connecting this input signal R of S and then this internal signal B. So we go like this. And then we have to show the direction of the signal. And then we have to name the branch. So in this case, the name of this branch is going to be the transfer function, which is G2 of S. Then we continue for this side also, right? So it's going to be the transfer function, the block with this transfer function G3 of S. So just like what we did for this side and this area, we are going to do the same thing too for this side. So we connect these two nodes and then we show the direction of the signal and then we name it to this transfer function, which is G3 of S, right? Now we are done with, we are halfway done, of course. So the second part is to connect the internal signal to the output signal. And the only way to do that is, we have already seen this, how it's already done. So we just connect the node A to the output node, this. And then the transfer function, we show the direction of the signal. And the transfer function is plus or minus 1 based on the polarity here, right? So it's plus or minus 1, plus or minus 1. Now the real question here is why 1? Right? Why 1? Now you can actually, from what you've seen so far, you've seen that the transfer function of just any branch is 1, right? And then the question, it actually begs the question, where exactly is the transfer function that we are talking about? So the transfer function, just imagine it to be the transfer function of any line in a control systems diagram is 1, right? So let's just take it this way, that we are trying to find the transfer function of this whole line right here, and it's 1. And then the B2 will do the same thing. The transfer function of this whole line right here is 1. So we connect it to the output and it's plus or minus 1. Right? And then we continue for this side to we show the direction of the signal, and then we name the branch with the transfer function of 1, right? So based on what I've done right now, we can form rule of thumbs, right? The first one, or the first rule of thumb I could say, is if the first one is, if we have signals moving away from a node, it's signals moving away from a node signifies a pickup point. Signifies a pickup point, right? And it makes sense here. So you have this node, right? This node right here, and then you have these signals moving away from it. So this node here signifies that there is going to be a pickup point, which we have seen here, right? So the second postulate is signals moving to a node signifies a summing junction. You can illustrate that one to here. This node right here, we have this signal going in. You have that one to going in, and you have this going in. So it means that this node or this output is an output of a summing junction. So once you have these two as your fingertips, of course, you can actually reduce any control system diagram to the signal flow equivalent. Okay. Now, the third form that I like to show you is the feedback form. And we all know how the feedback form looks. So the feedback form looks like this. You have a summing junction with an input signal of R of S. The polarity here should be plus, just in case. And then you have the error signal going into a block or a system with a transfer function of G of S. And then you have the output signal C of S. Since the feedback formula, you have to draw some feedback. Going into a block H of S. And then it comes back to the summing junction minus or plus. Now, how then do we convert this into the signal flow graph? So the first thing to do is to identify your internal signals, right? So we already know the non-internal signals of which is the input R of S and then the output C of S. So the second thing is to identify the internal signals. So I'm going to name this my internal signal as A, right? And then there's no need to name this one because it's the same as the C of S, right? And there's no need to name this one too because it's the same as the C of S. I can be tempted to name this one. So this signal right here, right? And there's nothing wrong because it's a different signal on its own. Let's name it B. In fact, let's go technical and name this E of S to show that it's an error signal. And let's go this way and name here E. So these are our internal signals, our E of S, then our E. So you've done half of the work by identifying the internal signal. So the second one is to try and convert it into a signal flow graph. So we are going to use this thing that we found here, that signals moving into a node signifies a summing junction. Now, this is where most students get confused, you know. So this is a summing junction, and I have signal E and then signal R of S moving into the summing junction to form the error signal E of S, right? So the trick here is let's first draw the nodes and let me show you what I'm about to say. So the first node here is that of the R of S, right? And then the second node here is that of the E of S. E of S. And then the last node here is the output, which is C of S. And then this node here is right below the E of S. So we do the same here. And then we write A here. Now, the trick with the summing junction is that, see, the summing junction, you have two signals coming into together to form an output signal. So the thing is, you have to draw it in such a way that it lands on, I don't know how to say it. It's like the node here, the signal here, you have to draw the branches like in a way that it lands on. So this one has a transfer function of 1, and then this one also has a transfer function of 1, right? So since this signal is moving into this node and this signal is moving into this node, then it signifies that the signal E of S is going to be the output of a certain summing junction, which is somewhere here, right? I don't want to confuse you that much, but let me see it one more time. Based on the thumb rule, the second thumb rule here, right? We said if you have signals moving into a node, then it signifies the presence of a summing junction, right? And then the output of that summing junction is the node, is the signal of that node, right? I hope I'm making sense, right? So if that's the case, we've been able to identify the internal signals, and then we've been able to write the systems with a, I've made a mistake here. Okay. Showing the direction of the signal, and then this branch has a transfer function of 1, right? And likewise to this branch has a transfer function of 1, and it's either minus or plus, depending on what you choose here, right? So this transfer function is either minus or plus, depending on what you choose here. So from there, we move on to this side, right? So this side, we join the error signal to the output signal, and then we showcase the direction of the signal, and then we name the branch with the transfer function of that system. And then from there to we join this. You see, this is a pick-off point, right? So it's going to be the same signal. The signal here is going to be the same signal here, right? So there's no need for us. So can just connect this node straight to the signal node A. Connect it like this. And then the transfer function of this branch, right, is the transfer function of this block here. So it's going to be H of S. Right, so now you can simplify this whole thing, right? You can just multiply the transfer function of this by the transfer function of this, and you get an equivalent of H of S, C of S, G of S. This signal is error signal of S. Okay. Okay. Now then we again prove our first postulate that once signals moving from here, let's move on to an example to try and illustrate everything I've said so far. So we are going to be using the same questions that we did when we were learning how to reduce block diagrams. Let me pick the easiest. Okay, this is the easiest. So for the advantage of signal flow graphs is that you don't have to be moving blocks like the way you've been doing when you were trying to reduce block diagrams there, like manual way. So the first step is to identify our signals. So this is our input signal, R of S, and this is our output signal, C of S. The next step is to identify the internal signals. The internal signals, I can name them the way that I feel. So this signal here is A, right? And then I always advise you to always search for the forward path. The forward path is the straight path from the input to the output, right? So in this case, the forward path is going to be the straight line from this input sound to this output, right? And this whole path here becomes my forward path. So the most economic the most advisable thing to do is just search for the forward path and then I identify all the internal signals from there. That would help a lot. So in this case, I've seen that my forward path is what I just identified. Then I'm going to identify all the signals from there, right? So I can see that I can name the signal here to be B, right? And then if I move along the forward path, I can also name this signal along this branch as C. If I move along the forward path, I can name this signal as D. And then if I move along the forward path too, this is already named, which is C of S, right? Now the next step is to draw the nodes, right? So I'm going to draw the node or the input signal. The first node here, and then I name it R of S. And then the second node, A, I name it A. Then the third node, B. Then the fourth node, C. Then the fifth node, D. And the next node, which is C of S. Now the next one, I'm still on the forward path, all right? So you try and identify the systems on the forward path. So let's start. So this is a system with a transfer function of 1, right? Then based on the postulates that we have seen so far, we said if you have signals moving into a particular node, then it signifies that the signal on that node is going to be the output of some summing junction, right? So the first system that we have identified is this branch right here. Then it has a transfer function of 1, of +1 because of the plus here. So we connect it to the output of this summing junction, which is A. And then the transfer function of this branch is going to be +1. Right? And then the still on the forward path, right? So the output of this, so don't see the output. So the output, the A here, right, connects to the next signal here through this system here, right? So then we connect it that way, and then we show the direction of the signal, and then we name the branch with the transfer function G1. Then we move on to that way too. So B is connected, signal B is actually connected to node B is connected to node T via the system G2. G2. Right. And then here, the output of this summing junction is D, right? So it means that we are, based on the postulate that we've said if you have signals entering into a particular node, I'm always going to repeat this. If you have signals entering or moving to a particular node, then that node is the output, right, of some summing junction present. So this node is a signal D, right? And that signal D is the output of this summing junction here. So we are going to draw this C to D. Then what's the transfer function? Of course, it's 1. Because the transfer function of every branch in the control systems diagram is 1. It's 1 right here. Right. And then I move on to the next one. So from D to the output C of S, I actually have a system of transfer function G3. Right. Now, if you don't really understand anything, you can just rewind and play the whole thing again. Okay. So now I've been able to identify the forward path, which is what I've done here. So straight from the input to the output. Now the next thing is just to identify all the other signals, and based on what you've done so far, we have simplified the work for us in a way. Okay. So let's move on. From this signal A, sound to the summing junction, right? We can draw a particular line or a curve to block D. So from A, then we draw the curve to block D. And then it has a transfer function of 1. Now, again with our postulate that we said that if we have signals moving into a node, then the signal on that node is the output of that of a particular summing junction here. So D is the output of this summing junction here. And then we have 2 signals, this one and this one, moving into the D node here. So it means that the signal on that particular node here is going to be the output here. Now, mind you, most of you might make the mistake of trying to connect this one to this side. Okay, although it may seem right, what I'm trying to say is that you are trying to say that the output C, right, or the signal C is the output of the summing junction, right, so, which is not the case, right? So we can see that the signal C is clearly an input to the summing junction here, right? And then the D is rather the output. So if you do something like this, you are trying to connect the node A to node C. You are trying to see that the signal on this node, which is signal C, is the output of the summing junction, which is not right in a way. So you somehow have to shine your eyes when you are doing these things. Okay. And let me clean this one. I'm going to say it one more time. We have connected this signal from node A to the node D, because node D is the output of the summing junction here. And based on what you've seen so far, we've said that if we have 2 or more signals moving into a node, then the signal at that node is the output of the summing junction, which you have seen here. So don't confuse yourself that much, right? Okay, wait. So now we've been able to draw this into the signal field equivalent. Now the next one to draw is this one right here. Right. So we are picking from signal B, then we are sending it to the output of this summing junction right here. So signal B is right here, right? So we take it and then we send it to the output, right? Let me draw it well. Send it to the output right here. And then the transfer function of this branch is going to be minus h of s. Minus because of the sign here. Right. Now, mind you, I did not move or I did not draw a curve between B and R of S, right? I did not do that because if I do that, then I'm trying to see that the output of this summing junction right here is the R of S, which is not the case. Clearly from the diagram, you can see that the output of this summing junction here is A. So if I should move or if I should draw the curve from this node B to node R of S, then I'm trying to see that there's a particular summing junction here, and then that summing junction has an output of R of S, which is not the case from what we are seeing here, right? So the appropriate thing to do is to draw the curve from the node B. Is to draw the curve from this B to the node A to signify that the signal at this particular node here is the output of the summing junction here. So now you can see that this and this are the inputs of the summing junction here, and then the node or the signal at that node is signifying the output of that summing junction, right? So you have to take notes of all of this, and then the pickoff points here is being shown that this is moving away from it, and this is moving away from it, right? So those are the postulates that we actually said at the beginning of this video. And then you can actually clean your your signal flow graphs. This one right here looks not clean. So to do it, you can multiply the transfer functions of this and that, right? So G2 times G1 gives you the G2. So then you can draw a straight line from B to D, right? You can just do away the node C, right? To actually make everything look nice for you. So let me draw how the thing should look finally. This minus H of S, this node A, this node B, and then this is node D. And then the transfer function here is G2, because you multiply G2 by 1, and then we have G2. The transfer function here is going to be G3, and then the signal here is C of S. And then we move from A to D. The transfer function is 1, and then R of S. Right. Now I'm being tempted to see that. Now one might be tempted to see that why can't I just multiply R of S by 1 and then have the node here? Well, I actually don't know. I am not an expert yet in control systems, so I can't boldly say that you can multiply the R of S by the 1 here to actually merge this and this together. I can't actually say that. So for the meantime, I urge you all to, stick to this. That if you have anything, the input signal, then the output signal, just stick to it. Plus it makes the whole thing, easy for you to understand. So I know some of you are asking the question now, why can't I multiply the R of S by the 1 here? Like I said, I don't know everything in control systems here, so I urge you to just leave your diagrams like this. Okay, so if you feel like I've made a mistake here, you can draw by the TE's office, then we can discuss it. Or I'll be at the library third floor, and I can just come and let's discuss. So the next one that I'd like to convert to signal flow graphs, I'm searching for the simplest one that we can do. Then we migrate to the more difficult ones, and then let's see how everything goes from there. So so let's start with this question again. So the first step to convert any block diagram into a signal flow equivalent is to identify the forward path. Now the forward path is just a straight line from the input to the output. So in this case, our input is the R of S signal here. Then our output is the C of S signal here. If I should draw a straight line from this to the output C of S, then this right here is my forward path. Everything on this path here, that's my forward path. Okay, so we've done well trying to identify our forward path. Now, the second step is identifying your internal signal on the forward path, right? So the first internal signal that I like to identify is the signal right here. So let's name it A. Then I move along the forward path. Then I identify another signal here. Let's name it B. Then I move along the forward path. I identify another signal here. Let's name it C. I move along this side. I identify another signal here. Let's name it D. I move along and identify another signal here. But then I can't name it because it has already been named, which is C of S. Right. So the second step here is draw your nodes. So my first node that I'm drawing is the input signal R of S. R of S. And then the second node I'm drawing is the internal signal A. And mind where I'm placing the names, right? I'm not placing the name here, or I'm not placing the name here, or I'm not placing the name here. I'm coming. Okay. I am not writing the name of the signal here, or here. Because by all means, I'll be drawing a line to connect it, and I'll be sending the line from here to here. So it's always advisable to write it at the top right, or top left, or top down, or top. Don't write it where I've written it. Okay. So I'm writing it here. And then the next signal is this right here, B. And then the next node is the C. Then the next node is the D. And then the next node is the C of S. Right. Okay. Now I just have to connect them, right? So right now I'm just focusing on the forward path. Okay. So let's try to focus on the system on the blocks. So on this input signal, the system here is this branch right here. And then the branch has a transfer function of +1 because of this plus here. So I connect it to the output of the summing junction here, +1. Then from the signal A, it actually passes through a system of transfer function S. So then I connect the node A to node B. And then I indicate the direction of the signal. Then I name this branch S. Then from the node B to node C, it's a block or a system with a transfer function of S. So then I connect the node B to node C. Then I indicate the direction of the signal and I name the branch, which is S. Okay. Now, the output of this summing junction here is D, right? So it won't make sense if I just say that I'm stopping here to just connect C to C of S straight, right? So it means that the signal C, right, is an input to this summing junction, right? So then I have to connect the C to the D, right? And then I show the direction of the signal. And then it has a transfer function of 1 because the transfer function of a branch in control system is just 1. And it's +1 because of the plus here. Okay, it's +1 because of the plus here. Okay. Now from the D, I move on straight to the C of S. Then the C of S, I indicate the direction of the signal. Then I name it with the transfer function of the system over there, which is 1/S. Now I'm done with the forward part. So the next thing to do is just to concentrate on these ones and that one. So the thing that I would like to concentrate on is picking a curve from the node D straight to the input of this transfer function here. Okay. So I move on to my node D, right? Then I draw a curve from the node D to node A. Then the transfer function of this branch right here is -1 because of the minus. It's -1 because of the minus here. And then it's 1 because the transfer function of a line in control systems is 1. So 1 multiplied by minus here gives you -1. Okay. Now, why don't I just take the curve from D and take it straight to R of S? It's like I've been saying, if I should take the curve from D to R of S, then I'm trying to see that there is a summing junction here, right? And that summing junction, the output of that summing junction is R of S. But from what you are seeing here, the output of that summing junction is not R of S, it's A, right? So taking the curve from D to this summing junction, or taking the curve from D to A, signifies that the node A, the signal on this node, which is A, is the output of a particular summing junction there, right? And then based on the postulate that we've seen so far, we actually said that if you have signals moving into this, or signals moving into a particular node, then the signal at that node is the output of that summing junction. Okay, so drawing a curve from D to R of S won't be right. Okay. Now I'm done with this side. Let's concentrate on this side. Okay, the signal coming in from this side. Okay. So the signal coming in from this side, you can tell that it passes through this block here, this feedback block here, then it goes straight to the output function. So it means that I have to take a curve from the output function here and then take it to the input of the summing junction over here, right? So I take it from here, and I draw it, and I take it to node A, right? And then the transfer function of this branch here is going to be -S because of the transfer function of this block here is S. And then the input to the summing junction is minus. So when I multiply both of them, I get -S, right? And then it actually makes sense because we have this branch moving into this node, and we have this branch moving into this node, and we have this branch moving into this node. So the signal on this node should indicate that it's an output of a summing junction, and that's what we have seen here. So the output of the summing junction is this signal here, A. Okay, that's great. And then the next thing that I want to represent is this signal from this side to this summing junction here. Okay, so I can take it from, so we are taking it from a pick-off point here. So what we said of a pick-off point is that if you have two signals coming out of a node, then there's a pick-off point at that node. So I pick the curve from node A, then it's going to end on D. And then the transfer function of that branch is going to be plus 1 over S. Now, I'm not taking this branch and I'm not bringing it here, because that would indicate that C is going to be the output of a particular summing junction. And from what you are seeing here, C is never the output of this summing junction, but then is the input. But D is rather the output, right? So instead of trying to draw the curve from A to C, we have to draw the curve from A to D, because D is actually the output of the summing junction there. So it makes drawing of this curve wrong. Okay. And then it actually, says everything that we need to know, because you have this and this coming together to form the output of the summing junction. And then we have this one coming outside to indicate a pick-off point. And then we have this coming outside of the node A, and this coming outside of the node A to indicate a pick-off point. And then we have this coming in, this one coming in, this one coming in to indicate a summing junction. Okay. So now afterwards, you can clean your signal flow graphs to make it more presentable. So how we do it is that we can multiply the transfer function here by the transfer function here by the transfer function here, right? So if I should do such a thing, I'm coming to draw the final one, and it's going to be C of S node B. So we've gotten rid of node B and C. So this is going to be node A, and then straight from B comes to -1. And then the transfer function here is going to be S squared, because S times 1 is S squared. And then the transfer function here is going to be 1 over S. And then this side goes to this side, and you get minus S. And then this side comes to this side, and then you get 1 over S. And then you have R of S, and then 1 here. Okay, great. So this is how your signal flow graph should be for this particular block diagram. Let's move on to the next one. Let's move on to this one. This one is a little bit complex. So the first thing to do is identify your forward path. Right? So the forward path is a straight line from the input to the output, right? So this whole thing here is my forward path, right? Then after I've identified my forward path, I have to identify my internal signals. So my internal signals is going to be the signal here, A. Then I go ahead of this block, B. Then I go ahead of this summing junction, C. I go ahead of this block, okay, D. So there's a pick-off point. It shows that the signal on this branch right here is going to be the same, right? And I go ahead of this block, E. I go ahead of this block, and that's the output function, the output signal right there. Okay. The next step is to draw it in a signal flow graph form. So I first of all take my node, and then you can pause it and try your luck and see. And then you can pause the video and try your luck and see if you actually get the same thing that I'll solve. But if you don't get to, I've shown you where we mostly are. You can just come by and then we talk things out. Okay. So this node right here is the R of S. And then the next signal is A. All right, it's here. The next signal is B. The next signal is C. The next signal is D. And the next signal is E. The next signal is the R2 signal C of S. Okay. Now, the next step is to link the nodes. So the signal A here is the output of the summing junction here. So it means that I'm going to have a certain input to this particular node here. So the system at the R of S here is just a branch. And we know that the transfer functions of all lines or branches is just one. So I connect the R of S to A, and I name it, or I show the direction of the signal, then I name it +1. It's +1 because of the plus here. And then from there, I move on to the signal A to B. I link the node A and B. I show the direction of the signal. Then I name it with the transfer function of this system, 1 over S squared. Okay, so from B, there's C, right? So signal B is the input to the summing junction, and C is the output. So like you already know where I'm going with this. So from B to C is the transfer function of 1, because the transfer function of every line is 1, and it's +1 because of the plus here. So 1. Then from C to D, from C to D lies a block of transfer function 50 over S plus 1. So I connect from C. Then the name of this branch right here is 50 over S plus 1. So from there, I move on to E. So I connect the node D to node E. I show the direction of the signal. Then I name this branch after the transfer function of this block here, because it connects the D and E. S. Then from here, there's a summing junction. And then the summing junction, the output of that summing junction is the C of S. Right? And then the input is the signal E here. So we draw E. Transfer function of 1. Because the transfer function of a branch is 1. Okay. Now we are done with the forward part. So the rest becomes easy for us. Okay. So I'm going to take this long shot from this side to that side over here. So it's obvious that it's on a signal C of S. So we have to take it from the node C of S. So we take it from the node C of S. And then it has to be on A, because A is the output of this summing junction here. And then based on what you've said so far, we said if 2 or more signals are moving towards a node, then the signal at that node is the output of that transfer of the summing junction there. So I take the curve here, I draw it to A, then I name it, I show the direction of the curve, then I name it -1. minus 1 because of the minus here, and then the transfer function of a line or a branch in control system is 1. Now I did not draw from C to R of S. Because if I do that, then I'm trying to say that the output of this summing junction here is R of S. And based on what you are seeing here, the output of this summing junction is not R of S, but it's A. Okay. Now, the next thing to do is to draw the signal from D to the input of this summing junction here. Okay. So since I'm taking it from this side, then I'll start from D. Now the output of this summing junction here is C, right? So I have to draw it from D to C. From D to C. And the transfer function of this system here is 2 over S. So it's going to be minus 2 over S because of the minus here. So minus by 2 over S gives you the minus 2 over S. Now I'm going to draw from D again. Then it passes to this side to the input of the summing junction here. Okay. So how it's going to be done is that I have to take it from D, then draw it to the output of that summing junction, which is C of S, and then name that branch to be minus 2. Okay, it's minus 2 because of the minus here. So this is it. Now I can clean my signal flow graphs to actually make it more presentable. So I can multiply 1 over S squared by 1, right? And I can multiply S by 1. Okay, now what you shouldn't do is multiply this by this. It's not actually, yes, I mean your conscience won't sit right with you if you try to multiply this by this. And then the rule of multiplying is make sure that there's nothing separating. So let me just take an instance. If this were to be here, then I wouldn't multiply the S by the 1 because of this branch here, right? So that's why we are not trying to, that's why we are not multiplying the 50 by the S here. But then we are just trying to multiply the 1 over S by the 1 because there's nothing here, and there's nothing there or something like that. So just take note of this one. Okay. So the final signal flow graph is going to be, I have my R of S, my node A, and my node C, my node B, and my node C of S. This D, this C, this A, this R of S. Okay. Let me share my screen. Okay, I'll share my screen. Okay, so that's transfer function of 1. And then from here to here, that's a 1 over S squared by 1 over S squared gives you 1 over S squared. And then from C to D, you have 50 over S plus 1. Then from D to E, you have S times 1, which is S. Then from D to C of S is just minus 2. And am I sharing my screen? Well, I'm sharing my screen. Okay. Then from D to C is minus 2 of S. Then straight from play a long ball from C of S to A, and then I have -1. Okay, so this is how your final one should be like, but I don't think it matters. If you can't simplify, don't force yourself. Just can still use this, and then I'm sure when you use the Mason's gains, you by almost get the same thing. Okay. Now the next one, show someone around here. Done this. Okay. So the first rule is identify a forward path. So this is my forward path. Okay, that's the first step. The second step is to identify the internal signals in the forward path. So A, I move ahead of this block. B, I move ahead of this summit junction. C, I move ahead of this block. D, I move ahead of the summit junction. And it's already named here, right? The next step is to write the nodes. So node R of S, node A, node B, node C, node D, and node C of S. And feel free to pause if you feel like you can solve it, because I've solved like three examples. So I'm sure you've gotten how you've gotten a feeling of how the whole thing should look like. So from this node to this node, you already know it's 1. From this node to this node is G1. And from this, let me draw the G1. Then from this node to this node is +1. Then from C to D is G2. Then from D to C, that's 1. And it's +1 because of the plus here. All right, so now we are done with the forward path. Now let's concentrate on this long branch right here. Okay. Now we are taking it from the node A to C. So we play a long shot. Then we take it from to node A. And I missed. Okay, so C now scored. Okay, and then the name of that path is going to be plus G of 3. It's plus because of the plus here. Don't make that mistake. It's plus. If it were to be minus, then would that be minus? But in this case, it's plus. So we have to put plus there. And then we are done with that particular part. So the next one to concentrate on is from this side to this side. So I take it from node C of S. Then I play a long shot to node C. Let me draw the curve to node C, right? And then the name of that branch, I show the direction of the signal, and the name of that branch is going to be -J4. And it's minus because of the minus right here. Okay. And it's on the G and it's on the C to show that it's on the, the signal here is the output of the summing junction. I'm sure you're conversant with that one by now. So the third one to draw is from this side to this side. Okay. So again, I take it from C, I play a long shot to A. And then the name of this branch is going to be -H. It's minus because of the minus here. Now you can decide to tidy up your whole thing by multiplying this G1 by 1 and then this G2 by 2. But then what you should never do is multiply these two, the one here by G2. We can't actually do that because there's a line, we are actually picking off something here. So it's not actually possible for us to multiply this transfer function with that transfer function, or also actually get it wrong. So we are going to multiply G1 by the 1 here, and then G2 by the 1, 2 here. So the final thing that we should get is going to be this, that R of S. We have A, then it goes to C with a transfer function of G1. Okay. And then this goes straight to node C of S with a transfer function of G2. Then from node C of S, we play a backpole to node C, the transfer function of G4. And then from C of S, we play a long ball to A. And then with the transfer function, wait. Okay, let's see something. I think I made a mistake. Okay, so it's the same thing. So the direction is from node A rather to node C of S. Okay. Then from node C, we play another long ball to A. And then we name it minus H. And that's it. We have tidied up the whole thing. Okay. Let's go on to the next one. This one is tricky. This one is tricky, but it's actually very simple. They've named your internal signals for you. So there's no need to fret. But let's go to the next one. I want to show you something. Okay, this. So there's nothing too difficult about it. So all you have to do is just identify your your forward path transfer. Just identify for your main forward path. Okay. So the main forward path is from here to here. Okay. And then you start naming your internal signals. So the internal signal here is A. Ahead of this, I have B. Ahead of this, I have C. Ahead of this, I have D. Ahead of this, I add E. Ahead of this, to the output. So there's no need for me to rename it again. So the main forward path is for what we have here to here. I haven't tried this yet, so I'm just solving it on top of my head. So if you feel like I've made a mistake, I've shown you where we are. So you first identify you draw the node R of S, A, B, C, D, E, and then C of S. Okay. Now we draw, you know that from here to here, as a transfer function of +1 is +1 because of the plus here. From here to here, you have of plus G2 is plus because of the plus here. Then from B to C is just 1. Then from C to D is plus G5. G5 is plus because of the plus here. Then from D to E, transfer function of 1. Then from E to C, it's a transfer function of G6. Okay. Now, the next one is to draw from here to this side. It's lagging. Okay. So it means that I pick from C, then I join it to A. Right? The output of the summing junction is A. So I join it to C, then A. Then the name is going to be minus J1. It's minus because of the minus here. Okay. Now the next is I can also draw from this side to this side too. I don't know why it's lagging. Okay. So from C of S straight to the outlet of this summing junction, which is E. And it's -1. It's -1 because of the minus here, and then the transfer function of this line or this branch or this path here is this is 1. So I can also take it from this side to this side. So from C, then I draw a long board A. Then it's going to be minus G7. It's minus because of the minus here, and it's G7 because of the transfer function of the system here. Now, the part that is going to be tricky is going to be this part. That's why I want to save the best for last. Now, it came in your midterm, I know. I told you to solve it and come and show it to us, but I think only one person came. So how we do this is, I try to break it down to you that you can redraw this thing right here as G3, the same thing function with G3, right? And this will down to G4, so the summing machine, and so keep it, and then you have this just a sketch. And then from this side, you can also split it. So you can split it in this way. You can do it this way. And it won't change anything because it's all the same. It won't change anything because it's all the same. So you realize that this whole place is a parallel form. There's class and there's class here. And this one too is a parallel form on its own. Right? So how I do it is that I'll take it from A, right? From A, then I go to the outlet of this summing junction, which is C. So from A, play a long ball or maybe a true pass to C with a transfer function of class G3, class G3. Okay. Then I take another one to from A, the same A, right? So I have to draw another node here just to signify something. So let's create an arbitrary node here. Okay. Then I can take it from A, then let's name here F. Let's name this node F. I can take it from A. Then I can also draw outlet here and name here G4. I hope I'm making sense. It makes sense. Then begin from the same A. Because I'm taking the transfer, I'm taking it from A, right? So I can take it from A again. Then draw it to the same F. and name it G3 again. Then the output of this F goes to E, the transfer function of 1. All right, I hope I'm making sense. So when I'm cleaning this whole thing, I can clean it in such a way that I can bring, wait, let me go through one more time. Okay. Now I'm cleaning this whole thing, I can clean in such a way that I can say that this is my R of S. Then 1, this is my node A. G2 times 1 is the same as G2. G2. Then I move it from this side to this side, minus G1. Okay. So now I can actually just sum these guys up, right? So G2 plus G3, can just write both of them here, G2 plus G3. We wouldn't change a thing. And I could also sum this and this one, right? Because it's actually going into a summing junction. So G3 plus G4, then I multiply the whole thing by 1, right? So let's continue. This node C, then node E, G5, to G6, and draw it from here, minus 1. Okay. And then from here to A, minus G7. Okay, so like I was saying, I can just sum this one up, G3 and G4, and then multiply it by the one here to just give me one branch of G3 plus G4. Okay. So this is what you have. Like I said, I haven't solved this. This is just on top of my head. So if you feel like you have anything else that I can contribute, you know where we are. Okay. The next one, is it a complicated one? Okay. Let's try this. This is like assignment, so just go and draw the signal flow graph equivalent of this, and then come and show it to us. If I'm not in the TA's lab, then I'll be at the library, third floor. Yeah. So let's move on to the complicated one that I said, this one. Okay. So you identify your main forward path, which is from here to here. Okay. Then after I've identified it, then you identify your internal signals. Okay. So this is V1. They've already named the internal signals for us. V2 of S, V3, V4, V5, and C of S. Right. So I'm not even going to concentrate on this and that and that. Right, because it's going to make my whole thing plenty. So this node is of R of S. This node, that's V1. Let's forget about the V of S. And then let's forget about the of S. And then the next node is V2. The next node is V3. The next node is V4. The next node is V5. And the next node is C of S. So the next thing is I just try to connect all these nodes. And based on the things you've seen so far, I connect here, I get the transfer function of +1. It's +1 because of the plus here. Then from V to V2, I connect the nodes, and then I get a branch with the name G1. It's G because of what's here, and it's plus because of the plus here. And then from V2 to V3, that's going to give me 1 +1. It's +1 because of the plus, and then the transfer function of this is 1, right? Okay, from V3, then I connect it to V4. I get plus G2. Then from V4, I connect it to V5. I get +1. And then from V5, I connect it to C of S. Then I get G3. So I'm done with the main forward path transfer function. I just have to concentrate now on the feedbacks and then all of that. So the first thing that I'm going to concentrate on is this, from here to here to that. So like I've indicated here, it's going to start from C, and I play a true pass to V5. Right? You already know why it's V5, and if you don't know it, you can always go back to the previous examples and I've explained them. It's minus H3. It's minus because of the minus here. Right? So the next one that I'm going to concentrate is from V3 sound to the output of the summing junction here. To V3, then the output of that summing junction is V5. Play a true pass there. Then I get, oh, wait, let me not confuse you. Okay, from V3, it's above. So from V5, then I get plus 1. 1. Okay. And then from here to here. So from V4 to the output of the summing junction, which is V3. So from V4 to the output of the summing junction, V3, I get minus H2. Okay. Then again from V4 to the output of the summing junction, V1. So from V4, I play a long ball to V1. Okay, let me connect it to V1, and that gives me minus H1. It's minus because of the minus here. Then I think that's it then. Yeah, that's it. Is it? Yeah. Okay. Now you can do cleaning. I don't, yes. And then the only thing that you can clean is the G1 multiplied by the 1 over here. And then when you do that, you are going to get a simplified version of this R of S, and that V1 straight to V3, straight to V4, straight to V5, C of S, and G3, 1, G2, G1, and 1. Then moves on from V3 to V5, 1. It moves on from V4 to V3 minus H2. Then from V4 moves on to V1 minus H1. Then from here, and then you can't multiply this by this because it's branching from here. So these are some of the things that you have to take note of when you are drawing some things. And like I said, I don't know if when you multiply this by this, I don't have all the knowledge in control systems here, so just to be on the safe side, just leave it like this. Okay, wait, this goes in this direction. Okay. Now, the next thing now I'm going to talk about is the Mason's rule. The Mason's rule. You can take a break and then